let's start by recapping what we talked about yesterday, which was that when you sum the forces on an object and you get something that is a particular form, then you know that object is moving with simple harmonic motion. The form of the equation is that you have some sort of second derivative of a function with respect to time, or anything, and that equals negative some constant times that function again. This is generic, okay? This is true. This, if you can fit your function into some form that looks like this, then this tells you that there is simple harmonic motion happening. It doesn't tell you anything more than that, okay? When we want to solve the differential equation, we want to guess the solution, which turns out to be sinusoidal, okay? And as it turns out, you might find this to be interesting, every function can be written as some combination of sines and cosines of varying amplitudes and frequencies. Every function in the universe. Did you know that?
I do know.
Pretty cool, huh? Okay, sorry, hold on 1 second.
Are you here for the light test, right?
Yes.
Light.
I don't know, I heard it's pretty heavy. The answer's always 5.
Okay, so you can get a little bit more information from this equation because we know that the solution is going to, when it is simple harmonic motion, the solution to this equation is going to be something of the form x equals a sine of omega t plus phi. Okay, now let's talk about the parts of this. A is the amplitude, which doesn't actually directly have an effect upon anything in the motion of the object, okay, as far as acceleration goes. The sine tells you that it's oscillating back and forth. It could also be cosine. Sine and cosine are the same, right? They're the same exact thing, depending on what this phase shift is. This phi is your phase shift. It's how much left or right the function has been shifted. And omega is the thing that you get from the frequency. Okay, it tells you the frequency, but it's not directly. Omega is called angular frequency. But we learned it as angular velocity, but it's the same thing. Angular frequency, instead of frequency, is, it relates it to scaling everything to a 0 to 2 pi x-axis, basically. So instead of having frequency being in units of per second, we have frequency being in units of radians per second. Okay, so we have this angular frequency omega, which is in units of radians per second, and it is the same as angular velocity when something's moving in a circle, because something moving in a circle is obeying simple harmonic motion. So, radians per second, and then we have this phi, which is your phase angle, or phase shift. And then we have regular frequency, which is cycles per second, or omega over 2 pi. If I want to know how many cycles per second, it has nothing to do with radians, so I want to get rid of those radians. Okay, omega is in units of radians per second. It's how many radians on your sine axis. How many radians am I going through per second? Frequency is how many cycles per second. And then you have period. Period is how many seconds it takes to go through one full oscillation. Okay, and that's the same thing when you're talking about orbital motion. Period is how long it takes to go around in a circle. This is how long it takes to complete one full cycle. Okay, so this is period. And period and frequency are inversely related to one another. So period is 1 over frequency. And since frequency is omega over 2 pi, period is 2 pi over omega. Okay, and that's all related to the solution of this differential equation. Now, generically, if I want to know, if I know the solution to my differential equation is of this form, and I go back and take the two derivatives and plug everything in, I can figure out that this c value, this constant value, is actually equal to something specific from this equation. What is it? Well, let me take the first derivative, which is dx dt. And if I take the derivative of sine, I get cosine of whatever times the derivative of the inside function, which is just omega. Right? So I get omega a cosine omega t plus b. My second derivative is the derivative of cosine, which is negative sine, and it brings out another omega. So it's negative omega squared a sine of omega t plus b. So if I plug in those two things over here, the second derivative of position is negative omega squared a sine omega t plus b equals negative c, which is the constant that we're trying to figure out what it is, times x, which is a sine omega t plus b. If I cancel out the a sine omega t plus b and the negative sign, I get on this side omega squared, and on this side c. So generically, whatever is in front of the position function is omega squared. So, in terms of a mass on a spring, we said, okay, a mass on a spring obeys Hooke's law. Force is negative kx, and that equals ma. If I solve this for acceleration, I get a is equal to negative k over m times x. And if I replace a with the second derivative of position, I get d squared x dt squared is negative k over m times x. And because I know now, from doing this one time, instead of doing this every time, that the solution to this is going to be something that's a sine omega t plus b, I can figure out that omega, which governs how frequently the motion occurs, omega squared is whatever is in front of the x, or the function that is by itself. So in this case, omega squared for a mass on the spring is k over m. Which is how we got the equation, or how you figured out in the lab, how to figure out what k was. You figured out what omega was because it was in the function that was given to you. I think they called it b or something. Whatever this was, whatever was in front of your independent variable, that was omega. And that's how you got it, and that's where it comes from. That's why. That's why omega is equal to the square root of k over m. For a mass on a spring. But what if instead we're not talking about a mass on a spring? What if we're talking about a pendulum? What are the forces that are acting on a pendulum?
Gravity.
Definitely. And?
Tension.
Okay. So, in which direction is there motion?
Both X and Y.
Tangentially.
True, both x and y, which is why we don't use those. When we're talking about circular motion, we talk about radial and tangential. right? Is it into the center of the circle or is it along the edge of the circle, right? Because a pendulum is swinging through an arc, right? So if a pendulum is swinging through an arc, it's moving in part of a circle. Therefore, it's got an acceleration into the center or in the radial direction, and then in the tangential direction as well. Things don't always move in uniform circular motion. Sometimes you have a tangential acceleration too. Okay, and so what we want to do is figure out, first of all, the tension has no effect on the motion this way. Okay, the tension is affected by the motion this way, but it has no effect on it. It's the dependent variable in this. But the mg here has a component that's in the radial direction and in the tangential direction. And this is the tangential component here. This is the tangential component of my gravitational force. But here's the thing. It's changing, right? Because if this is the angle that the pendulum is at that instant, then this is also that angle. And this is mg sine theta. But then, an instant later, it's at a different angle. And therefore, the tangential force or acceleration is at a different point. Has a different value. So if I sum the forces on this in the tangential direction and set it equal to ma, it's mg sine theta equals ma. Okay? In the same way that we used the form of Hooke's law that had the negative sign, we use the form of this that also has the negative sign. And what that means is it's always pointing this way. Right? If I'm over here, I'm moving this way, but my acceleration is this way. If I'm over here, I'm moving this way and my acceleration is this way. Okay, so it means the negative sign that we're going to put on here means restoring force. It wants to go back towards equilibrium. So when we used Hooke's law, we used negative kx. When we use this, it's going to be negative mg sine theta. It's pointing towards the equilibrium point. So if I sum the forces, ma equals negative mg sine theta, the first thing I want to do automatically is what?
Cancel out the ends.
Cancel out the m's. Then what? What we would have done before is try to figure out a way to write A in terms of x, right? But we can't. We can't do it. Because A in terms of x doesn't help us. We want A in terms of theta.
Does it have to do with taking the second derivative?
Yeah, to make it alpha instead.
Both of you are right. Second derivative, but it has to be alpha because alpha is the second derivative of angle, right? So instead of A here, I want this to be alpha r, where r is the length of the pendulum string. That's where this is introduced into the equation. So this is now alpha L equals negative g sine theta, where alpha is the second derivative of theta with respect to time. And to make this look pretty, I'm going to divide by L on both sides to get this second derivative by itself. So, what's the problem? I'll give you a hint. There's a problem. Any guesses? Does anyone know what the purpose of ordering? You don't have the equation in the form that you want it to be in. You know that a pendulum is a simple harmonic oscillator. Therefore, when I sum the forces and do all of this magic stuff to it, it should end up in the form, the second derivative of some function right? It doesn't have to be x, it could be any function. The second derivative of some function is equal to negative omega squared times that function again. But I don't have that. I have the second derivative of some function, which is theta, is equal to negative some constant times sine of that function, not that function itself. This format and this format don't match. And it turns out that a pendulum is not a simple harmonic oscillator unless we make a very, very simple approximation. It's called the small angle approximation. Do you remember in your lab when I told you specific angles to use? They were small. It's like 10 degrees, 15, 20, maybe 25, right? That's getting pretty big actually. But I didn't say, start your pendulum at 90. And I did that on purpose, because if you do that, it doesn't work. The small angle approximation says that you can approximate the sine of theta to be something else when the angle is small enough. And it comes from the graph of sine of theta. If I graph theta versus sine of theta, it looks like this. Agreed? What if I zoom in on this part of the graph? It looks like a straight line. And the slope of that line is 1. Which means for small angles, sine of theta is equal to theta. If you have your calculator out, what is the sine of .1 radians?
0.09983341.
0.0998. So sine of 0.1 is equal to 0.0998. Okay, what's the sine of 0.11?
0.1977.
Okay, let's see how far we can take it. What's the sine of 0.25?
0.2474.
What's the sine of 0.5?
0.4794.
Okay, so you can see that even at sine of 0.5, which is like pi over 6, 30 degrees, right? The approximation is still pretty good. Sine of theta is about theta. Sine of theta isn't about theta. It's about theta. It's almost theta. Okay, it's a pretty good approximation. So when we are assuming small angles, what that means is I can call sine of theta, theta. And that gives me an equation that looks like d squared theta, dt squared equals negative g over L theta. Now, this is in the form of a simple harmonic oscillator. The second derivative of some position function, in this case it's a measurement of angle, is equal to some constant times that position function again. So, if I wanted to write out the equation for the angle as a function of time, it would be a sinusoidal function. It would be the initial angle, which is the amplitude, times sine of omega t plus phi. Where omega is the square root of g over L. And if you remember, omega is related to period. Period is 2 pi over omega. So period is 2 pi times the reciprocal of this, square root of L over G, which is what you found when you looked it up for your lab. All of that isn't just a made up thing. Like, let's just pick an equation for the period of a pendulum, it comes from this, summing the forces. Newton's second law, the most important thing in your whole life. Questions so far? Okay. Let's go back to, I want to talk to you again about the function. Let's go back to a mass on a spring or whatever, anything really, that follows this rule, A sine of omega t plus b. And if we're talking about a mass on a spring, how would you determine what the amplitude is? This is a representation of the position of that mass as it oscillates up and down or left and right or whatever. How would you determine what the amplitude of that motion is? Or what information would give you that? What does it mean?
Like you need the mins, the max and mins.
Yeah, you would need to know or be given or somehow find out what is the maximum stretched length or maximum compression of that spring. Where are its extremes, right? And usually that's at the beginning, right? It's pulled down by a certain amount, it's pulled to the right by a certain amount, or whatever. How would you find out what omega is for a mass on a spring? You would use the equation, which I think is on your equation page. How would you figure out the phase shift, the phase angle? Okay. You would do it using initial conditions, right? Because sine by itself, without a phase shift, starts at 0 at t equals 0, right? Here's my position, here's my time. This is what sine is if it's not shifted. So if you know what's happening at the beginning, then you can determine how far your sine is shifted to the left or to the right, right? If I'm starting at position 0 at t equals 0, then it's sine without any phase shift. But if I'm starting somewhere else, then it's not. Okay, it's going to be shifted by some amount. If I'm starting, instead of starting at position 0 at time equals 0, if instead I'm starting at maximum displacement, right? If you're using a pendulum or if you're using a mass on a spring, very frequently, the first thing you do is pull it back or pull it up and then let it go, right? Where does it start? It starts at maximum displacement. So what would be your phase shift, or what would you do to this function to make it something that starts at maximum displacement? Do you know what I'm saying?
Derivative equal to 0, maybe?
Okay, yeah, well, yes, to find that point. But you don't even need to do that, right? Like, so what I'm saying is if you want to get a pendulum started, there are lots of ways. If it's just sitting there and you hit it with a baseball bat, then it's starting at theta equals 0, right? And I gave it some initial upward swing. But more frequently, you're going to pull it up like this, some angle, small angle, and you're going to let it go. You're going to release it from rest, and then it's going to swing, and it's going to come back to its maximum position again. It starts and ends at maximum position or displacement. What is the function that starts and ends at a maximum? Cosine. So if that's the case, then either your phase shift is pi over 2, or you just call it cosine instead of sine, and then you're done. Okay? It's some sinusoidal function. How much it's shifted depends upon the initial conditions. Same thing with a mass on a spring. You pull it down or to the side as far as you're going to pull it, and then you let it go. and then it starts at maximum displacement, and then it ends at maximum displacement. That's not the only way to start something oscillating, but that's one of the ways to start something oscillating. Another way to think about it is, let's say that I do make this cosine. If I make this cosine, and I say, okay, it's a mass on a spring, and it's cosine, there is no phase shift. It starts at maximum displacement. If I want to know what is my velocity as a function of time, what would I do to this? I know you're struggling. I get it. This is position, and I want velocity. What do I do?
Derivative.
Take the derivative. Yeah, so if I take the derivative, that gives me velocity. The derivative of a cosine gives me negative sine, right? So it's negative a sine of omega t times the derivative of the inside function, which gives me an omega. Okay? The point being, when your position is at a maximum, your velocity is 0, and vice versa. That's why that's why you choose the sine function, but that's also why they're always opposites of each other. Okay? Because if you start at maximum position, I'm a pendulum, I'm starting at maximum position, that has to be when you're released from rest. Right? Conservation of energy says if this is my maximum position, this is my maximum amount of potential energy, I have to have the minimum amount of kinetic energy, which is 0. Okay? Cosine is a maximum when sine is 0. Sine is 0 at the beginning, right? So if I said this is the velocity function, what is the velocity at time equals 0? Sine of 0 is 0. So the velocity is 0 at the beginning. So that follows the sine function. Okay? The cosine says I'm at maximum displacement at the beginning. If I wanted to find the acceleration, I could do that as well. I could say I'm going to take another derivative of this, and that gives me acceleration. The derivative of negative sine is negative cosine. It brings out another omega. Negative a omega squared cosine of omega t. This number, whatever it might be, and this number, whatever it might be, are maximum at the same time. So when you are at maximum displacement, you have maximum restoring force. When you are at minimum displacement, you have minimum restoring force, or 0 restoring force. What if I asked you more specifically, what is the maximum value that velocity can be in terms of these variables? It sounds like a really hard question, but it's not. Because this part is the only thing that's changing. Amplitude and omega, angular frequency, this is simple harmonic motion. Frequency is not changing, right? These two things are constants. So sine is varying between 1 and negative 1, 1 and negative 1, 1 and negative 1, 1, 0, negative 1, 0, 1, 0, negative 1, right? What is the maximum value that this entire thing can become? If sine can only go up to 1 times a omega, right? This part can only go up to 1 or negative 1 times a omega. So the maximum value of the velocity is a omega. Okay, let's think about it in a different way. Let's say that we're going to use energy considerations. You've got a mass on a spring. Forget simple harmonic motion, and let's just go back for a second, last semester. You got a mass on a spring, and you pull it back some distance x away from, let's make it a little smaller, x away from equilibrium. So this is my x equals 0, my equilibrium point, and I pull it back. First of all, you know what's going to happen, right? It's going to move through equilibrium, compressed by the same amount, and then move back out to x, and then back in by x, back out by x, back in by x, etc., back and forth and back and forth. The question is, what is the maximum velocity? That's what I was asking you here. What is the maximum velocity using this equation here? My question here is the same thing, but if you didn't need or have any of the simple harmonic motion stuff, you could still do it using conservation of energy. Because if I pull something back by some distance, x, and I release it from rest, all it has at this point is elastic potential energy. 1/2 kx squared. When it moves through x equals 0, all of the elastic potential energy has been converted to kinetic energy. You know that to be the point of maximum velocity, because you know that's where the minimum potential energy is. So if I say, well, 1/2 kx squared equals 1/2 mv squared, I can figure out what my maximum velocity is. First things first, cancel out your 1/2s. And the next thing I want to do is point out that this x here is a special x. It's the amplitude of the motion, right? If you pull it back by some distance, it's not going any farther than that. It can't gain energy along the way. It's never going to pass this point. So if I were to graph this, this particular x value would be the amplitude of the motion. So instead of x, I'm going to call it a. So ka squared equals mv squared. So my v is the square root of k over m times a. V is a times omega, which is the square root of k over m, times sine omega t. It's the same answer. Okay? If you analyze it using simple harmonic motion methods or using energy methods, you get the same maximum velocity. You can do it with acceleration as well. I can say, what is my maximum acceleration? Maximum acceleration is when I have maximum displacement. Let's go back. ma equals negative kx. This is biggest when this is at its amplitude. So my maximum acceleration is negative k over m times when x is a. Or omega squared is k over m times a. If I asked you how much energy is in the system at any given time, you can always tell me the answer. If I say I pull some mass on a spring back and I let it go, and it oscillates back and forth, and all I give you is how far I pulled it back and what k is, then you can figure out what the total energy of the system is, because at this moment of release, there is no velocity. So you start out with this 1/2 ka squared, and that turns into some combination of potential and kinetic between here and here. But this is the total amount of energy of the system throughout the entire oscillation back and forth.